Good morning. Today is the first session for DBA Fundamentals in May, and we have a fantastic speaker today, Kendra Little. She'll be doing a session on index design patterns for beginners. We also have a couple of new people with us. Let me get into my slide deck real quickly and go through some housework or housekeeping. My wife doesn't think I like to do much housework. Okay. Our sponsor and our longtime sponsor, Century One, has fantastic products. Please do us a favor and go download a bunch of free products. You'll love that. Download Plan Explorer. That's free. The professional version. It's a great way to look at execution plans. There's tons of free content, free manuals, free questions, and then great products to download. So try that out. We have a new sponsor that I haven't had a chance to get into a lot of their stuff yet, but they do something similar. They do an enterprise-wide management, and I've downloaded some of their stuff, and I'm getting ready to test it. But you can go and try some of their stuff out. It's dbwatch.com. And this is virtual group news. I was informed that early on that I had been misspelling Shane's name on this screen at least for a full year, and I only misspelled his name on the front screen for 3 months. So I didn't keep all of my errors correct, but we have some new news. We have 2 new helpers, Glenda Gable, and that's her Twitter account, and Kevin Wilkie. I wanted to be sure I got his. I think that's his correct Twitter account. You can tweet them, and they'll be helping us along. They're going to initially start out working with our sponsors, but they'll be helping us and doing more things in the future, and because this just gets to be a whole lot. It really does. We have a contest going on for the first half of the year, and to be entered into the contest, you must be a member of PASS. You must be a member of our chapter. You must be a Twitter follower, and you must be subscribed to our YouTube site. Then you get 1 entry for each session that you attend through the year, or through the year till June the 30th. And at the end, we'll draw a 3 users for a $1,000 Amazon gift card, a $500, and a $300. We have another contest. We're all about contest and education, apparently. For the past Summit 2018 registration, every group, every local chapter, and every virtual group has this code, or has a code that will give you a $150 discount. The one thing that we do extra is we give away $500, a $500 Amazon gift card in a drawing of all the users that used our code. We get to give away a free PASS Summit comp for every 20 uses, and in the last 3 years, we've given away about 7 or 8 full comps, and we try to get as many as we possibly can. And this year we're shooting for 60, so we can give away 3. Here's some of our sessions coming up, and some sessions from other people. Down under, those sessions count too as far as a session entry in our contest, and that's one of the reasons we do that. It makes it easier to figure out stuff since we have 2 semi-chapters working together. The Women Technology chapter has some great stuff coming up, and Saturday Night SQL does too. Actually, look like they've got the same one, unless I put this down wrong. I may not have, but go check that out in both places. Women Technology, Cloud. Okay, I may have got something wrong on that. Go check out those chapters. Great chapters. There's tons of great virtual chapters. Every language, just about every major language, in just about every topic you can think of, and we duplicate some stuff. There's tons of great education out there. SQL Saturdays are one-day events in your area, usually almost right in major cities or fairly close, where you have speakers come in. really good speakers, sometimes new speakers that are still very good, and sponsors pay for everything. The only thing you might have to pay for is your lunch, and that's, you get a ton of great education and exposure. Go to SQLSaturday.com and find out the nearest one close to you. Join Pass to grow to your career. Go check it out, and that's part of our contest. You got to be part of Pass. So people that see this from the internet, if you want to be part of that contest, you can join and be able to win some of our gift cards. And this session will be recorded and available within a couple of days on our YouTube site, dbafuntube.org or dbafun.org. You can get to it either way. Today, we have Kendra Little, and she has a new endeavor she's been working with for a couple of years, SQL Workbooks. It's fantastic. You need to really go check it out. I know she doesn't brag about herself, but Kendra's one of the better teachers and speakers out there. I was thinking about it today as I was coming in. I was thinking, it's like when you read a great blog post and you get at the end of it and you say, I really do understand that now, and I can't believe I didn't understand it before, because it's so simple explained this way. Kendra does that with so many sessions. You just really need to check her stuff out. So anyway, she's a very well-known speaker. I'm going to turn it over to Kendra now. Here you go.
All right. Thank you so much for that nice intro. So let's see if I can get my screen to show. So make sure that, yep, it wants to show the correct screen. There we go. And I want to actually play PowerPoint so we can get started. We're going to spend most of our time in demo today, but we do have a couple slides to start out with. Let's just make sure that my webcam is, okay, my webcam should also be showing. So here we go. We're going to go ahead and get started with index design patterns for beginners. I'm Kendra Little from SQLWorkbooks.com. And today we are going to talk about how do you design a non-clustered index in SQL Server, even if you're a beginner. And we're going to walk through an example, and I'm going to challenge you to come up with a design of an index. Now, doesn't matter if your design is right. It doesn't matter if your design is wrong. The way to get good at designing indexes is to practice, and getting started is the first step. Now, if you want to get the demo code to play along with this video or live webcast, depending on when you're joining us, you can get the demo code at SQLWorkbooks.com/index design. Notice that that is lowercase. Right now, that URL is case sensitive. So what we're going to do is we're going to look at a query, and I'm going to challenge you to design an index to make it faster. Specifically, I'm going to challenge you to design a disk-based row store non-clustered index. Now, that's a lot of words all together at once. Basically, what we want to see is how fast can we make this query with just a classic non-clustered index in SQL Server. And when I say classic, what I mean is it's not column store. It's not in-memory OLTP. And it's not that those things are bad. It's just that in order to compare these sort of more advanced new technologies with our existing indexes, we want to get good at existing indexes too. So your challenge will be to design one non-clustered index to reduce the logical reads that this query does as much as possible. And I'm going to show you how to measure the logical reads and compare your indexes. Your index will need to have at least one key column, and optionally, you can use included columns as well. That demo script that you've got there, it contains both the problem query and it runs through all the different solutions that we are going to compare today. So once again, we're talking about disk-based row store indexes, and that is our challenge today. The table that we're looking at is called ref.firstname. It's a really small table, and on a table this small, measuring duration isn't that effective. So measuring logical reads makes a lot more sense. How many steps does SQL Server have to take to get to the data? We want to make that as small as possible. Ref.firstName right now, it simply has by default a clustered primary key on the first name ID column, which is an integer column. And what's in this table? Well, in this table is information from the Social Security Administration in the United States. They give out a free data set on data.gov that has information from all of the Social Security number applications that people file when they have a baby. And they provide aggregate information about baby names in the United States. Ref.firstName is part of a larger sample database that has that baby name information. And this just has a unique list of all the first names with the first year they were reported, the last year they were reported, and the total name count for them. And this has data right now through 2016. Soon we'll be getting an update to the data set. They release it around Mother's Day every year. So here's the query that we are challenged to index today. And I have the schema for ref.firstName on the side of the table. I call these one-year wonders. What we're querying from ref.firstName, and to keep it simple, right? This is index design patterns for beginners. We don't even have any joins in here. We've just got a query. And we're saying we want the first name, the first report year, and the total name count for names where the first report year is the same as the last report year. In other words, this name only appears in 1 year, and at least 10 babies have this name. We're going to order the results by total name count descending. So what we want is babies whose name appears in just 1 year, where these two columns are equal to one another, and there are greater than 10. There are at least 11 babies. We don't have greater than or equal to. This is greater than 10. There are at least 11 babies who have that name. And we are going to return them by the babies who have the highest name counts, who meet this criteria at the top of the list. And our challenge is to design an index for this query. So I want you to take a moment and write down what you would do. You don't have to script out the whole create index statement. What I want you to pick out is what key column or columns would you use in your index? And if you want to do multiple indexes, as long as they're disk-based row store, that's fine too. Also, would you use an include statement? And if so, what columns would you include? So go ahead and take a piece of paper right now, or an index card, or a Post-it note, or a notepad on your computer screen. Write down key and look at the query. Pick out the columns that you would put in the key. If you want to figure out the order you would put them into, that's great. And then also, would you include any columns? And if so, what column? Now, I'm going to give you just a few more seconds. Just make a decision. If you're not sure, that's fine. Just guess. Because the truth is, when you start out with indexing, the way you learn is by guessing and then testing the index. And I'm going to show you how to test the different indexes. So, all right, now I've yammered on long enough. Make your final choice. Write down your key, and if you want them, your included columns. And we are going to now switch over. And first, we're going to baseline the query so that we can see how many logical reads does it do before we index it. And then we are going to test the results. So it looks like Management Studio is now showing up here. What I've done at the beginning of this script, this is the same script you have for download, is I have restored, I unzipped and then restored a backup of the database. There is a restore command at the top of the script. And it also does things like enable query store. If you're using a version of SQL Server that doesn't have query store, just it makes some notes where you can comment out those commands. So what we're going to do, we're going to use this database and make sure our virtual machine is awake. There we go. And now we're going to baseline the logical reads in the query and look at the execution plan before we do anything. I am going to click this button right here to say, show me the actual execution plan. This will show up after I run the query. So now I've run that, the button is outlined, and that's going to give me a map of how the query was run and tell me what indexes did it use, what operations did it have to do. So first off, running our query, I actually really think this data is kind of interesting in terms of the one name wonders, and I really kind of enjoy looking at it. There are some interesting names in here that I think are particularly fun to look at. So I'm kind of scrolling down to find my favorites. There's one in here that's Kendra. It's very similar to my name, but it's Kendrae. There's some of them that are just kind of interesting about the United States. For instance, in 1967, that was the only year that you were, likely to name your baby Twiggy, right? Kind of an interesting historical thing there. There's some fun names by year. Here's Kendra. Kendra happened in 1992, right? So my name just had an interesting variation, but it didn't take off there. And we also have, this is, I think, my all-time favorite. You can find your own favorites in this list. In 1978, there were 11 babies reported being named Travolta. We also had in 1979, we had babies named Starbuck. But of course, that didn't pick up after the coffee chain took off. There's also a history of babies named eBay in here. I'm going to leave it to you to look at the data so you can figure out if the babies named eBay were before or after the rise of eBay. But okay, it's a fun data set. I think I like playing around with it. But how did it actually run the query? That's what we're really after. Well, we haven't created any non-clustered indexes on the table yet. So there's only one index on the table right now, which is the table itself. The table has a clustered primary key on first name ID, which is named PK _ first name _ first name ID. So it had to scan that clustered index, look at all of the rows. And if I hover over the clustered index, what we see there's no seek predicate. This is a scan. There's nothing about seeking. We have the word predicate here, but it doesn't have the word seek in front of it. And when you see the word predicate on an operator like this, what it means is I checked every row and I applied this filter. So I had to read the row and think about it. Read the row and think about it. And what I was thinking about is total name count greater than 10? And is first report year, this is an equal to sign I crossed out, last report year. So this is another view of those predicates in our query. In our query, we have where first report year equals last report year and total name count greater than 10. And we can see that in the predicate on the clustered index scan. There's also a sort operator here. And if we look at the properties of the sort operator, it is sorting by total name count descending. That's the order by of our query. And we can confirm that it's having to order them as a separate step. Oh, we have some comments that Starbuck, the reason that Starbuck got names there was because it was a character in Battlestar Galactica around that time. Oh, that is awesome. I need to watch that clearly. I love it. You can see pop culture filtering into the baby names, and sometimes it just goes just 1 year. All right. Donaldina, by the way, in the 1920s, there were some babies named Donaldina, which is one of the weirder names I've ever heard. That did not catch on. 1920s, the Great Depression. Anyway, so the first thought for a lot of people, and myself included, when we first start indexing, one of the ways that seems like maybe it'll be the easiest way to index queries is, okay, I'm going to just look at all of these individual predicates, all these individual columns that we saw in that predicate that we can find either in the joins or the where clause. I'm going to create an index for each one of those. So I'm going to create an index for first report year. I'm going to create another index for last report year, and I'm going to create another index for total name count. And maybe the idea that we have when we think of this is, okay, well, maybe this will just be more flexible in the end because I don't have to worry about ordering the columns, and I can just create one index for each with each of them as its own key. And maybe that will work, and these little small separate indexes can be used for the query. Now, these create really fast because this table is really small. That's why we're working with this really small table. We can mess around, and it's real easy to create all these indexes. But is SQL Server going to use these indexes for me? I have my 3 indexes created. I'm going to run my query again with actual execution plans on. I still have this button enabled. And I don't have to do anything like a recompile hint. As soon as I create indexes for the table that we reference in here, SQL Server, the next time we query ref.firstname, it's like, oh, the indexes have changed. I need to think about how to run this query again. So I'm going to run the query again. And when I look at my execution plan, we're still doing that clustered index scan. Nothing has changed here. And I forgot to measure my logical reads, but I can do it now. This is basically our baseline, right? Nothing's changed. How many logical reads does it do using the clustered index scan? Well, I am running SQL Server 2017. And as long as you're running SQL Server 2014 Service Pack 2 and higher, we have these things called actual statistics that show up for the operators in the execution plan itself. If you're running an earlier version of SQL Server, you can use a command called set statistics IO on to get actual IOs, but it's for the entire table. With SQL Server 2014 SP2 and higher, we can click on an operator in the execution plan and say, okay, how many logical reads did this operator do? This clustered index scan had to do 473 logical reads. So that's our baseline. If we're just scanning the table itself, we do 473 logical reads. And we are trying to design an index that makes the query do the fewest logical reads possible. So definitely less than 473. Well, SQL Server doesn't want to use my 3 little indexes there. I can force them for sure. I can say, SQL Server, I am going to use an index hint. And a hint, this isn't really a suggestion. This is me forcing the indexes. I'm saying, okay, I really want you to use these indexes. And if I do something like specify an index whose name doesn't exist in this, let's see what I'm going to do. Estimated plan here with Control L. If I put something who doesn't exist in there, it says this index doesn't exist. And if I try to run this query, the query actually fails, right? So I have to be real careful when I force indexes. But in a testing situation, in a dev environment, this can give me a lot of information. I want to know, hey, SQL Server, what would happen if you use these indexes? Why don't you want to use them? So I've got my actual plans on. I'm going to run the query now that I am hinting indexes that actually exist. And I can see that, oh, this is interesting. We got a much more complicated execution plan this time. In order to use these indexes, SQL Server really had to do something fancy here. And if I look at the individual indexes, right now we're on, this one is on. If I look at the object name here, this is the one on first report year. Just on first report year alone, my actual logical reads is 505, right? It had to scan that non-clustered index that has all the first report years and read every first report year, which itself took 505 logical reads. Then it had to do a join, and it joined all that with the information from the non-clustered index that's only on last report year. On last report year, it had to do an additional 508 logical reads. So we're already at 1,000 logical reads or so. We're already doing more logical reads. What with these little bitty indexes, SQL Server didn't want to use them because it was like, okay, I want to find like the babies whose first report year is equal to last report year, and there's more than 10 of them, but like you've given me separate lists. You've given me a list of all of the babies with the first report year. You've given me a list of all the babies with the last report year, and then you've given me a list of the babies with the name count, and I have to combine all of these things. And it's combining all of these small individual narrow lists is really complicated. It would be easier to just go read one copy of the information about all the babies sorted by first name ID, and on every row say, okay, how many of you are there? What's your first report year? What's your last report year? And check them there. Actually using all of these separate lists is more complicated. So building a lot of little narrow indexes, SQL Server often will just not want to use them because it's more work to use them. So, all right. Let's go ahead and clean those up. So one index on each of the predicate columns didn't work out for us. Now, checking in with folks. Did you folks come up with different indexes? If you have an index that you'd like to share, you can put it in the Q&A box. I promise I will anonymize things. Your index will, no one will be shamed for their index if you want to share your index. Okay, we've got one of them that says first name ID, an index on first name ID, include first report year and total name count. So that index there is on first name ID. Now, my clustered index is my clustered primary key is also on first name ID. The table itself is all ordered by first name ID. And we don't have a column in our where clause in here on first name ID either. We aren't saying where first name ID equals X. Totally get why you'd want to put first name ID into the key. And this is actually a great index suggestion, because when I think of an index like that, what I want to do is look at the query and say, is that going to help me narrow down the data? Is the first, especially the first column in the key, is it going to help me go straight to the data that I need? We have another index that I'm trying to click over. Come on, go to webinar. There we go. We have another one that says on key on total name count, include first report year, last report year. Another one is key first report year, last report year, include total name count and first name. We've got another vote for total name count and then including first report year, last report year, and first name. We've got one who says total name count descending in the key first position and then first report year and last report year. Another vote for key first report year, last report year. So we've got a good array of them. And the good news is I have written up demos for a lot of these exact indexes. So I like this, guys, because you came up with the exact indexes that I wanted to test for this. So let's move our windows around here and zoom it out and test some of these indexes. So this one we're going to test. We did get some suggestions here. When you see indexing advice about SQL Server, one of the little tips that you frequently see is to put the equality columns first. The equality columns from the query. And what that equality means is look for the places in the query where we have a column equal to some value. And the idea behind that is, if we are in our query restricting our column to a specific value, then we can seek to that value in the index. Now we've got something here that I'm going to put a question mark around. We have something that looks a lot like an equality. We'll talk about whether or not it really is. Our query does have an equal sign. It says where first report year equals last report year. So we're going to follow that advice and we're going to put these columns from the what looks like an equality. I mean, it's got an equal sign and the first position in the key of our index. We're then going to take total name count, which is another predicate. Our general advice is put your predicates in your key, put equalities before inequalities. This is a greater than, it is a range, so it looks like an inequality to me, right? We're also ordering by it. We're going to go ahead and put that third in the key for this index attempt, and we're going to see how it does. So I create that index, and now will my query use it? Now, even when you're well past being a beginner, when it comes to indexing, the game of will SQL Server use my index, it never goes away because we're constantly trying to create the smallest index possible that SQL Server can use to make the query as fast as possible. And sometimes SQL Server won't use an index if we don't have the index cover all the columns in the query. You'll see what I mean and how to recognize that. So I've still got my actual plans on. Looking at my results, and by the way, I think that the issue with 1989, the reason that it's the top 4 here, isn't that people actually named their kids weird names in 1989. It's just that the late 80s, I suspect, were a really bad time for data entry quality in the United States. And that makes sense with the 80s, right? That totally makes sense. But SQL Server didn't want to use our index either. We have created an index on first report year, last report year, and total name count, and it's still doing a clustered index scan. And the clustered index scan, let's bring open our properties window, it's still taking 473 logical reads. That hasn't changed. It's the same old clustered index scan. Well, one of the things that, like we did before, if I want to know, hey, SQL Server, why aren't you using this index? If I have a test environment, and I'm even just going to do estimated plan here, I'm going to do Control L. And that says SQL Server, don't run the query, but show me the execution plan that you think you would use if you ran this query. If I force it to use this index, I can see it's going to have to scan the index. And I can confirm, it did use the index that I forced it to use. It would use the index that I forced it to use because this is estimated plan, right? I can see it's going to do a predicate on here and say, okay, the index is on first report year, then last report year, then total name count. So it's going to scan it. This is an index scan operator. And then for every row, predicate is a hidden filter if it doesn't have the word seek in front of it. For every row, it's going to check the total name count and then check if first report year equals the last report year. But then it has to go do this key lookup for every single row. It has a nested loop operator, and that means for every row that comes in, I'm going to go do this, what says here, key lookup. Well, what is it looking up? There's no predicate on this key lookup. It's not doing another filter check. It is seeking based on the first name ID. It has that information in the non-clustered index, but it's outputting the first name. The first name column isn't in that non-clustered index I created. So if I want to know, hey, why aren't you using this index? Sometimes just doing an estimated plan and forcing the index, I can say, okay, what are you going, is there a lookup now? What is the lookup doing? Does it have a predicate? Does it have an output column? Because, okay, you don't want to use this without that output column being in the index. Okay, fine. Well, I will add that column to my index. I'm now just changing my index a little bit. I'm still putting those equality columns first, but now I'm like, okay, first name, you were having to go look up the first name column. So right now I've got these, they look like my equality predicates. I'm putting those first. I've got an inequality predicate. I'm putting second in my key. I'm going to go ahead and now bring along the first name column for the ride. And to bring something along for the ride, we're not looking for a specific value in it. It's just in the select part. We're just pulling it back. We can include that. Including that means you don't have to put it at every level of the index SQL Server. You just need to put it in what's called the leaf of the index, the detail of the index, so that it's in the index, but nothing's ordered by that column. It's just tacked on and included with the other columns. All right, let's create this index. It's just got one extra column. Last time we had the same key columns. Now we've just added an include. Does SQL Server finally use our index without being forced? Well, now SQL Server does use our index without being forced. We have, here's our index, first report year, last report year, total name count, and then includes. SQL Server is using it. Well, okay, what is our IO now? Have we improved our IO? And I'm just going to close Object Explorer so I don't open it by accident again. There we go. So right now our logical reads are 443 logical reads. So, our logical reads isn't like awesome or amazing. We're at 443. It did use our non-clustered index, but it's scanning our non-clustered index. So we built a new structure. We put 4 columns in it, and now we're having to scan the whole thing and then sort all the data as well. Okay, well, let's learn more about our scan. I'm going to hover over our scan, and let's look at these predicates again. The fact that I don't have a seek predicate listed down here, nothing says seek predicate, means that this index, SQL Server, is not finding a way to seek into it. Our index is on first report year. That's the leading column of our index, first report year, and then last report year. But SQL Server is still having to check every single row and check, is the first report year equal to the last report year, and is total name count greater than 10? It isn't able to seek to the rows where first report year is equal to last report year. It's having to scan the whole thing. And to figure out why, let's look more at the structure of the index. our index definition, I have repeated right here, and we're going to refer back to that. But first, what I'm going to do, we're going to actually look at one of the data pages in the index. So this query right here uses an undocumented dynamic management view named sys.dmdb database page allocations. Technically, this is unsupported. It's real slow if you run it against large tables. This isn't something you would need to do in production ever. This is just like, okay, let's look inside our index to understand our index better for learning. So I'm looking at, I want a list of what are the allocated pages in this index for my specific index that I've created. I'm plugging in the name there, and I only want allocated pages. So this is going to give me a list essentially of the offsets of where is this data stored on disk in an 8K page. So let's pick a page here. We're going to pick page 52184. The next page in line is 52185. Now, they aren't always lined up like that. Sometimes we allocate over here and over there and over there. So I did want to check and make sure, okay, 52184, the next page, if I want to look at the next one, is incremented just one up. These are all in file 1. I only have one data file in this database. I'm going to plug these into a dbcc page command. Now, I am running first a trace flag for my session. It's trace flag 3604, and that means direct the output of dbcc page to, I typed messages tab here. Sometimes the results come back as a data set as well, you'll see, but it puts the output into my query, right? I don't have to go digging elsewhere in SQL Server. dbcc page itself is undocumented, but it is really well known in the SQL Server community. So I'm going to say, I want to look at a page in this database, in data file 1. Here's the page number, which is basically an offset, and return the data in style 3. You can play around with this. There's different formats it can return the data in. For an index page, data style 3 returns this nice little table where I can actually see for this page in the database, how is this actually stored on the page, which is really cool. So for this page, page ID 52184, right? All of these rows are for that page, and they're all in data file 1. Here are the different rows that are on the page. This is index level 0, which is the leaf of the index. And I can see that, I'm going to just recenter here. I can see all of the columns that are stored on this leaf page. First, we have first report year. That's the first key column I selected. And then we have last report year. And then we have total name count third. And notice that it is ordered by these in order. So first, things are ordered by first report year. Then they're ordered by last report year. So for 1971, we've got all of the rows for 2016 all together. And then those are sorted third by total name count. If I keep going on this page just has 1971 and 2016. If I go and look at the next page, let's go to 52185. I still have my trace flag on, 1971. Okay, and then here we finish up with the 2016s. That's the highest last report year we have for that year. So then we go to the next highest first report year, and the sorting continues. Here are actually the rows where first report year is equal to last report year. And then total name count is third, that's 5. Okay, we're only looking to total name count where it is greater than 10, right? So here is an actual row that would qualify for Katina and Valenci from 1972. Oh, 1972 was a great year for names, I think. So these rows would actually qualify. And you might wonder, why can't SQL Server seek to this? This seems like, right? First report year equals last report year. Total name count is greater than 10. Well, this is a tricky thing to seek to, because how does SQL Server know exactly what first report years it would seek on? Think about it that way. Our query says where first report year equals last report year. To seek on that, SQL Server would have to know, okay, I need a distinct list of all the first report years to seek on. Should I seek on -50 BC, right? Where should I start to figure that out, it would have to scan something based on first report year anyway, right? And if I'm already scanning something, I may as well, at that point, just look at the other rows on there and figure stuff out as well. So not everything with an equals sign is seekable in SQL Server because it can't just guess. It can't just use statistics to like estimate what it would seek on. It has to know for sure what it would seek on. And, you know, seeking on every year that might ever exist in the human calendar would be pretty inefficient. Okay, well, looking at the page, and this is sometimes if I'm really like trying to think through how an index would work, I'll look at what my keys are and I'll jot out sample data. I'll picture it in my mind. In this case, we've actually looked at the index itself, and looking at that data can help us understand how the index is used. Well, all right, so we're not going to be able to seek in this case on what looks like an equality, but is actually a special case. You know, in our query, because first report year and last report year are both columns in the index, neither of them is a specific value. This isn't seekable in the same way. So, all right, we had some guesses to say, I think we should put total name count as the index key, because we can seek to all the rows with total name count greater than 10. Plus, we've got total name count as the order by. Now, we had one suggestion to go ahead and put the descending in the key. Just for fun, I am going to put total name count first in this iteration of the index. I'm going to go ahead and keep first report year and last report year in the key. We're going to take them out of the key next and put them in the includes, and we'll compare performance on them. But so what I've got now is the index leads on total name count. The first column on the index is the primary sort order, so it's really important. So let's see if this index does better. We're still including that first name column. How does SQL Server do here? Well, SQL Server does use our index. If I hover over our index here, SQL Server does use our index. It's now the one that leads on total name count, and we now have a seek predicate. It is seeking on total name count greater than, and it is converting my 10 to a big int because total name count is a big int, but it's doing the implicit conversion on the scalar value itself. Now, you may hear implicit conversions are bad. What people are usually meaning when you hear what implicit conversions are bad is implicit conversions on the database column itself are bad. It's kind of a complexity in there. In this case, we are still getting a seek. The reason that implicit conversions are bad, they can burn extra CPU and they can prevent seeks. We're actually still getting a seek on total name count there. We are still having to do that predicate. We're having to do that filter where we actually think about every row and check first report year equals last report year. Putting them second and third in the key didn't magically make them seekable, right? But we are now able to seek on total name count. And let's look at how our logical reads are doing here. Our actual IO statistics now says that we are down to a new low, and a new low is good. A new low isn't bad. We're down to 334 logical reads. So we've actually made the query more efficient. And notice that the index seek operator is gone. Our query is ordering. Let's bring up our query onto the screen. Our query wants the results ordered by total name count descending. I created my index with total name count, and I didn't specify here. So total name count, if you don't specify, it is ascending. So let's look at our index. Our index is total name count ascending, so from low to high. But our query is total name count descending, right? It was still able to use the index. And the reason it was able to use the index is that it is able to do, if we look at the properties, the scan direction is backwards. Now, there are some limitations around backward scan. If SQL Server decides to do a backward scan, that portion of the plan can only be single threaded. But then in this case, that's really all I need because the object is small. So my performance is still very good. My logical reads are still very low because SQL Server can read from the end of the index. So I like that suggestion to tailor the index to the descending. Sometimes you can get away without doing it is all I'm showing here. Sometimes we And that's useful for making indexes work for different queries, some of which may use descending and some of which may not. All right, well, let's take a look at the internals of this index. Getting a page list, this time for this index, and let's pick a page here. Let's pick 61047. The next page, if I want to look at the next one, is one page up. So I'm using that dbcc page command. And sure enough, here, total name count is the first column in the key. So it can go to the portion of the index that's total name count 11 and just start reading the index up for there. It does still have to, for every row, say, is this value equal to this other value there? So we're sorted first by total name count, then by first report year, and then by last report year. And we can see here as this goes up to 2014, now we go down to 2015 there. I think it's really cool that we can actually see sample data from the index when we look at these pages in the leaf of the index. Names, by the way, only get reported in this data set if there's at least a minimum of 5 babies with that name, which kind of is interesting when you look at these names to know that there were at least 5 babies who had that name in the given year. Oh, I like the name Lawless. I like that. Is that after Lucy Lawless, maybe? I'm not sure. Is she a wrestler? Now I'm like, I don't even know who she is, and that could be a totally inappropriate reference. So I apologize if it's inappropriate. I don't actually know who I'm referring to. I should be careful about that because I have no idea where I heard that name, but I do read things like Reddit where who knows what popular culture I'm ingesting there, probably horrible things. All right, let's go back to safer territory. Things where I do know what I'm referring to is SQL Server. All right, I'm going to use the baby names database again, and this time I am going to refine the index a little bit. What we have been seeing by looking at the execution plan is that first report year and last report year, when I put them in the key of the index, there is still a predicate on there. Not a seek predicate, but a predicate on there. So SQL Server's still having to do a filter every time. That means the fact that they aren't seekable means they aren't benefiting me from having them in the key of the index. Having them in the key of the index can make the index structure itself slightly larger because when a column is in the index key, it has to be at all levels of the index. So if I move them to just the includes down here, that means SQL Server will only put them into the leaf level of the index. Oh, I got an update. That was Xena Warrior Princess. Oh, thank goodness. It's really dangerous when I hear anything about pop culture because I'm so pop culture ignorant that I'm like, I don't even know what I'm talking about. But okay, cool. I do admire Xena Warrior Princess, the show. So I'm glad. So now I'm moving those columns down to the include section of my index. And let's see if our included column version of the index will be used in here. I still have my actual plans on. And now I still have an index seek on there, right? If I hover over this, my seek predicate is still on total name count. My predicates are still on first report year and last report year. So it's the same as before, but I got away with moving them into the includes. And if I look at my logical reads, my actual IO statistics, I am down. I have shaved off 1 logical read. So I have made it, just by shrinking the upper levels of the index a little bit, I've made it ever so slightly more efficient by moving these columns into the includes of the index. If we want to look at a sample page from this index, let's go ahead and just gaze admiringly upon the real internals of our index before we wrap up in the slides a little bit. If we gaze at the internals of our winning index, here we are. You might notice something funny, and you may have noticed this before. I just didn't address it before. Our index definition has 1 key column, total name count, right? I'll go ahead and make that bigger up there. Here's our index definition. Here's our key column, total name count. We have 3 included columns, right? They're right here, and they're includes. They don't say key, but hey, there's another key column there, first name ID. That's because this non-clustered index is a totally separate structure. First name ID is the clustered primary key on the table. So we didn't specify first name ID anywhere in our index. And in fact, our query doesn't use it. Our query doesn't have first name ID in there anywhere or anyway. SQL Server will sneak the clustered index key into the end of our index keys if our index isn't unique, because it needs to secretly have a way to find the related rows in this index, and it needs to have a unique way to identify every row in this index. So it is normal that when we are looking at the internals of the table, we're like, hey, we didn't ask for this column in our index. There is a reason for that. Behind the scenes, SQL Server is doing it, even though in this case, our query doesn't need it and our query doesn't care. So, all right, let's pull this all together. What are these index design patterns that I'm talking about? One pattern, the first pattern, and I try to really focus on this. Whenever I'm thinking about designing an index, I look at the query and I say, what are the seekable predicates? Now, I'm going to look places where there's an equal sign. I'm going to look for equalities to seek on. In this case, and then sometimes you may have to do this. Sometimes you may have to do some testing to say, how good is this seek? How much does this narrow down the data? That's another way of saying how selective is that column. So if this query, in other words, said where first report year equals 2016, that might be a seekable predicate, right? Because SQL Server could say, oh, I'm going to go straight to the 2016s. This time that it didn't end up being seekable because we've got two columns on there, and it's like, okay, what values do I seek on? Okay, I'm going to have to check every single row anyway. So in this case, our seekable predicate was total name count. But that pattern of, okay, I'm going to try to find the seekable predicates, and I'm going to try to find the best seekable predicate to put first is really, really what I look at when it comes to doing an index. When an index is seekable, this is a drawing of just an index tree. Our index has had way more pages than this. But seeks, one important thing to know about seeks is they may be large. In this case, in this drawing, it's seeking more than half of the index. In our case, it was actually seeking a little more of that. Just because something says seek on it doesn't mean it's only reading a few pages, right? We only got this down to 300 and some logical reads with this type of index. Now, spoiler, there are other tricks you can do with more advanced indexing that can get this down to way fewer reads. That's sort of a fun extension topic that you can challenge yourself with for this query too. Another pattern is to look for portions in the query that are requiring sorts and to offload that. In this case, we're ordering by total name count. Total name count also is a candidate for, right, that leading column in our key. And one of the cool things about indexing is that we can, by specifying key columns, we can physically guarantee order in the index. Now, there is a little controversy around this. The controversy is that you'll see in some places where folks are like, okay, you shouldn't order in your SQL Server. What you should do instead of this is you should return these rows to your application server and then make your application server do the ordering. So don't put order by in the query. The reasoning for this argument is that the licenses on your SQL Server are generally way more expensive than the licenses on your app servers, and you can scale out those app servers more. So if this query was run really, really frequently, we might want to cache it in the application layer. We might want to push the ordering out to the application layer. So sometimes if we have the ability, we can ask, hey, can we move this order by out of the SQL Server? Sometimes we can't do that. Sometimes the query has a top, and removing the order by would change the sense of the query. Sometimes we just don't have the ability when we're tuning things in the SQL Server. We don't have the ability to change the application behavior, and we're just stuck with it. If we need to do the ordering in the database, leveraging the keys, like we got the sort operator completely out of that query because the index leading on total name count, actually the SQL Server, when it runs the queries, it knows when it's reading the data, it knows what order it is in because that was, in our case, the leading column of the key. So looking at the order by and asking, do I have to do this order by in the SQL Server? And if I do, can I use my indexing to order the results, to pre-order the results in the index structure can be helpful. The third pattern, cover with includes when needed. Remember when SQL Server just wasn't using our index? What we did is we tested and we said, okay, I'm going to look at an estimated plan forcing you to use this index. What do you go look up? What's the output column you're looking up? The first name column wasn't in our index, and without first name in our index, SQL Server didn't want to use it. Also, first report year and last report year, because they weren't seekable, in this case, they made sense as included columns as well. And this is just a little image that shows that SQL Server can be really clever when it comes to included columns. Not only can it be suitable for things that are in the select list, but if it's something it can't seek on, it can look at those included columns and do a comparison on them. Think about each one. In this case, it's looking at them and saying, is first report year equal to last report year? Is first report year equal to last report year? And this diagram shows that those included columns, they are only in what's called the leaf level of the index, the pages of the index that actually hold the index data itself. Those top levels that contain keys only, they are useful for navigating and sometimes seeking, hopefully seeking to the correct data, the data that we want to find in that index. Well, that's really a lot of stuff. Here it is all on one page. The patterns to think about as you start designing indexes. You're not going to be perfect, but I'm not. That's fine. The more you tune indexes, you'll just tune harder queries and things still won't be perfect, but it gets to be, it's like riding a bike. It gets to be more fun. But these are the things that I still focus on. What are the seekable predicates? Do I need to cover the included columns? Do I need to make the index larger with included columns to get SQL Server to use the index? You don't always. Sometimes you can get SQL Server to use your index without covering all those included columns. It's really cool. So I try to make the smallest index possible that SQL Server will reliably use. And then also, is there an order by in the query that I can offload? And I look for sort operators in the execution plan to say, are there sorts in here that maybe if I index them, it will take care of them. All right, so thanks for attending this. I'm going to start looking through the questions now. That link to the demo scripts again is sqlworkbooks.com/indexdesign. And let's see if we've got questions here. So Chad asks, Chad has an idea. Would it be possible to create something like a computed column for just the index? You can put a computed column on the table. So that's an interesting, the way that I have the challenge set up in the more advanced solutions for this, I actually don't have one with a computed column, but it is an interesting one to try. Pros and cons of computed columns. One cool thing about computed columns is that they can have statistics generated on the computed column that can help the optimization process. You can also index them sometimes. You can index them if they are, what's the word I'm looking for? Deterministic. If your computed column is considered non-deterministic, then it cannot be indexed or persisted. The gotcha I always have to think about with computed columns, well, there's many gotchas with computed columns, but one of the ones is you have to think about, do people run queries with select star against this table? Because if I just start adding computed columns, they may start getting back columns they don't expect, which depending on what they are, if it's an application server, that could cause problems. And that is the biggest reason historically why, using computed columns has been difficult for me, is because everybody's like, oh, I don't know, there might be some select stars out there. There is another way to do this. I would encourage you to test out both filtered indexes and index views. I don't want to give away too much, but there is a way that you can offload that computation. And what I'm going to do for this is I'm going to create a free course on SQLworkbooks.com and set this up with kind of the beginner challenge and then the more advanced challenge at the end, because I think there are a ton of fun ways to approach this and try it out. All right. Let's see here. Interesting question about a rewrite. Is there a way to use first report year minus last report year equals 0 in the where clause and include a seekable difference in the index? So this question is, if rewriting the query where we have a, and let's actually, I actually do want to, now I'm gonna exit out of here and go back there. I think this is a fun one to actually show on the screen. Let's go here. So the suggestion is this, right? So let's see here. I still have my last index on there. Now my last index on there isn't going to be seekable because that's the one with the includes in it, right? So I'm going to drop this index and I'm going to go back up and I'm going to create one of the earlier indexes that we had. So we're going to create this one that has first report year, last report year, total name count, and we're going to turn on actual plans here. We're going to go ahead and use this. And what we get here is it's still, you know, it adapts this, but it's still not SQL. And generally, if you do have like arithmetic in there, even if one of them is a literal, if you have arithmetic in your predicates, generally SQL Server has a really hard time with having any sort of math problem in your predicates. Totally get why you would want to check it. Like, is it actually going to help? But in my experience, that one generally not as much. So comment/question. This feels like we created a custom index for our specific query, and that's exactly what we did. When should we start thinking about the reusability of an index? I've seen plenty of databases that have a gross amount of indexes tuned to a single query. So this is a great question. We did very much act as if this is the only query that would ever use this table, right? And that is usually not the case. For certain tables, that may be the case, but it's rare. One of the things that I think is useful to do, though, is to not, like, we can do this wrong both ways. We can create indexes, you know, that are near duplicates or duplicates where we're indexing for different queries. That's one extreme. The other extreme is we can also go too far trying to anticipate what queries might run against the table and create these indexes that aren't really useful for anything. So the way I would sort of meet in the middle, right? We want to have the fewest indexes to have the best workload. We want to tune for the most frequent queries and the most important queries that run against the database. And sometimes these aren't the same. Like sometimes we have a query that's just a really critical query, but it only runs every once in a while. And maybe that query should have huge influence over index shape because it's so important, because of the purpose it runs for. It needs to be lightning fast. And then we may have other queries that are just really frequent, right? So for those queries, we want to create the best indexes. When we're just starting out, if we have very few queries, I would index for those queries. When we create an index, we want to look at other indexes on the table. And we want to say, is there an index that might be suitable for me that's similar? It might not be the perfect index for me, but it might make me fast enough. So look at the existing indexes on the table. In this case, we only have the cluster primary key, right? And say, can this index be good enough for me? Maybe I just need to add one included column if my query isn't already using it. So that would generally be my approach. I would also ask the question, is this query either frequent enough or important enough to get indexing attention as well? And we just kind of assumed that in this case, because in this case, we're really just learning the design patterns for designing an individual index. Yeah, but great comment. I love that. That's totally true. Question about designing column store indexes. So column store indexes are quite different because the order in which you specify the columns doesn't matter at all. And that's just because it's really its own session because they are totally different. So I love that question. It just requires at least its own hour to answer it. But it is a totally separate design pattern here. For the extension exercise, what's the lowest logical reads you've managed to obtain? I think I got down to 14. I'll have to check, but I think I got down to 14. It's in a different script, or I would try to secretly look it up, but I think I got down to 14. And I was just using rowstore. I haven't tested in memory OLTP or column store for it. Column store would have high logical reads, but but different CPU, because with column store, the goal is to scan compressed data. All right, folks, so I have gone 3 minutes over. Oh, will the scripts be made available? Let me put that URL back up on the screen. If you go to sqlworkbooks.com/index-design, all of the scripts are there. And when I create the free course related to this, there will be a link to that as well. The scripts are actually in a gist. So there was a question of whether they are in a GitHub repo. They are actually, they're in a gist, but the gist is embedded in the web page there because gist URLs are like unique identifiers. They're not so easy to remember in your head. So it's much easier for me to build a blog page and put them in there to make it memorable. So thanks so much. Thanks for joining me on this Tuesday. It's been really, really fun. And thanks to the folks in the database fundamentals group for having me. It's been really fun. So I am going to, let's see if I can actually get my internet working here and bring up the dbafund.org YouTube channel at the end here. Fundamentals YouTube. Somehow I'm not getting the URL right, but here we go. I think I actually have the page up here. So lots of other stuff to check out on their YouTube channel, and there is the subscribe button. Somehow I wasn't subscribed, but see, I fixed that. You can fix that too. Oh, and look, you can see my other subscriptions over here. I'm not ashamed to be subscribed to the Topi the Corgi page. Or there's other good ones here. Homer McEwen does fun music videos that are SQL Server themed, Kill a DBA. So shout out to Homer as well. All right, guys. Thank you for letting me know about Xena, Warrior Princess. Almost a wrestler. Love it. Almost a wrestler. So I got to run now. Thanks a bunch, folks. Have a great day. Bye-bye.